Okay, so what was the result that you got?
Sir, y cap is coming out to be 20357 plus 23284x1 minus 73x2.
Let's see if that's the case. So our equation is this on my end. Y is equal to 7.76 plus 0.91 plus 0.0044x2. I think you have done some mistake. Let's review the question. The question was that you have to first find a multiple regression line using the least square error fit, and in that you need to put the formula that we used yesterday. We found that, and that was this formula, the highlighted one: beta hat equal to x transpose x whole inverse into x transpose y. So using that formula, we have to find all the values, and the data set is given to be x1, x2 are the two columns which are independent variables, and y is dependent on the first two variables. So using this table, we will be solving for all the values of this beta 1 hat, beta 2 hat, and beta 3 hat. Uh, for that, we need to find few things. And because this beta hat is equal to these three components, x transpose x whole inverse, x transpose and y. So we will be first focusing on getting these values. X is given to be 111, 733, 560, 220, and 340, and it has been got from these things. 111 is consistent as the first column, as a, you can say that it is kind of a uh, constant value that has to be given in the matrix. And after that, the 733 is x1 column, and x2 column is this 560, 220, and 340. This is whole of x, and x transpose can be found easily then, because x is given, so x transpose will be this one, and x transpose x, if you solve it, you will get this value. If you are not getting this, maybe you have made some error. Then after that, you will be required to solve for this beta hat. Putting all the values in this, you will get this value: 7.7696, 0.91, and 0.0044. So these are the three betas: beta 1, beta 2, and beta 3. And putting these beta values into this equation, y equal to beta 1 plus beta 2 x1 plus beta 3 x2, you are getting these three values. And if you put the values of x1 and x2, which was asked in the second part, that you have to compute the delivery time when 4 cases are stocked and the distance traveled by car is 80 feet. So two values of x1, x2 will be 4 and 80. And by substituting these two values, you will get the value of 11.8 as the value of y. That's the final prediction that is done, right? And this is how this numerical was required to be solved. After that, if you have any doubt in this, you can ask right now. Otherwise, we will move to the next topic. Irshad, what was the mistake that you made?
Sir, I got it. Sir, it's here 733 and I have taken 732.
Oh, I told you to take the screenshot yesterday of this question, and I have also put this in the video. I have uploaded that.
Sir, otherwise I have done the same procedure.
Okay, okay. Next time, take care of the exact value. Okay, use the same values that are in the question.
Yes, sir.
Okay. And okay, then let's move to linear regressions, gradient descent optimization. So this is part 2 of it. We have already discussed the simple linear regression as well as multiple linear regression, in which we have discussed the role of single variable of x and multiple values of x in terms of array x1, x2, x3, and all of that has been discussed. Now we will be trying to do the optimization of the same, that in what way the equation will be optimized so that we can have the minimum cost. So let's say, I mean, this is kind of a summary of simple linear regression, in which we had one independent variable and one dependent variable, x and y. So using this equation of y hat equal to beta naught plus beta 1x, we calculated the cost function in the previous lecture of this j of beta naught beta 1. And we saw that this was the mean square error function, mean because we are doing 1 by n. Error is y by I minus y hat. So that has been expanded, and square was done because we wanted to uh, kind of make all the errors in the positive scale, because error might be negative also. So this was the reason we did the squaring. Now we know that the cost function is a function of beta naught and beta 1. So let's plot this cost function as a function of beta 1 considering beta naught. Uh, and I mean, we will be using these two to make the plot in 2D. So this is kind of the table that we are getting. So what we have done here is, uh, so considering only beta 1, because in this equation you can see that beta naught is a constant. So I mean, irrespective of the value of beta 1x, beta naught will kind of very w- its contribution will be very low overall, considering, let's say that there is a array of x values 1 2 3 4, maybe up to million. So this beta naught will be having very low contribution. So in a way, only beta 1 has been taken to make the plot. And in this case, what we are trying to do is we are making the plot between beta 1 and the j beta 1. And for that, we have done the substitution of multiple values of beta 1: 1.5, 0, 1.5, and 2. So these five values have been substituted, and we have plotted everything. I mean, we found these values. The values came out to be 0, 1.67, and everything has been plotted here. And you can see that, I mean, this is a bowl shaped thing, okay? And you are hitting the minimum where the where this mean square is 0. Mean square error is 0. I mean, this j beta 1 is hitting 0 for the value beta 1 as 1. So when beta 1 is 1, this equation is giving result to be 0, and that's the minima. And all other points are having more value, and it means that there is more mean square error at those points. So this is kind of a plotting way. I mean, we this is a way that we can plot the function between this beta 1 and the cost function of j beta 1. And that has shown us that depending on different value of beta 1, the cost function is coming out to be bowl shaped. In this case, this is parabolic function. So moving from here, we can um, we can say that this bowl shaped in 3D will look something like this, right? And if you plot this left hand side figure in 2D, so you will be able to see that it will be something like this on the right. And every time you are going outer from the center, the elliptical shape will come up. I mean, if you can visualize, if this left hand side figure is converted into 2D, and we are seeing the projection of this plane on the bottom, so it will look something like this. And we can say that this contour that we are plotting, uh, it is kind of a elliptical in shape. So that has been written here also. This is surface plot in which we are uh, I'm looking at the 3D plot, which is bowl shaped curve with only one point of minimum. The bottom point, at this point, it will be, uh, 1 second, I will highlight. So at this point, it is hitting the bottom, right? And same thing is here in the center, the red dot in the center on the right. So that is the minima, and all the other points are kind of going away from the center, and that plotting has been done in the form of contour. So gradient descent optimization, it is a optimization algorithm for finding the local minima of a differentiable function. Obviously, we have to do some differentiation. I mean, we have discussed this, that we are having, let's say, j beta naught beta 1, and then we had to do the differentiation with the beta naught ones and then the beta 1. So different betas were, I mean, kind of differentiated with the function. And same thing has to be done for n plus 1 number of betas. So gradient descent is simply used to find the value of a function's parameter that that minimize a cost function as far as possible. And can anyone tell me that what is the meaning of this argmin? Anyone? What is the meaning of this argmin function? And there is one more function, argmax. Can anyone tell me what is the difference between these two? Quickly.
Argument.
Yes. जल्दी बताओ.
Global minima with the army.
Yes. Can you please repeat?
Admin gives global minima.
Argmin gives global minima. Okay. And argmax gives global maxima. So actually, when when you will be using this in Python, argmax, let's say I'm talking about argmax now. So let's say that there is a there is this 1D array in which we have values of maybe 5, 10, 2, 3, 1, and we apply argmax function on this array. So what will it return? Can anyone tell? Obviously, if I apply max of this array, let's say this was ARR array, and if I apply max of array, the answer will be 10. But what will be the output if I apply argmax of this array?
It will keep the position of maximum.
Yes, yes, yes. That was what I wanted to hear from you. That argmax gives the location of the maximum number, and similarly, argmin gives the location of the minimum number. I mean, in this case, it will give us the location of the global minima. As she said, uh, this argmin will give us the global minima, but the location of it. Okay, so it is based on minimizing a convex cost function and tweaks its parameters uh, iteratively to minimize a given function. So we will, I mean, we will be kind of going towards the local minima in this, and it considers the gradient of a cost function to tune the parameters. And I mean, this has been written that gradient is kind of a slope of the function, and then the higher the gradient, the steeper the slope. So if we visualize this thing, let's say that this is the function that we have. So if it is more steep, obviously the gradient is higher, and if it is less steep, then the gradient is low. That we all know, because dy by dx is the slope, right? The change in y based on x. So that's the slope. And in mathematics, a gradient is a partial derivative of the function with respect to its inputs. Let's see what's happening here. So let's say we are starting from this point beta naught. At this point, I will change the color because it is already red. So let's say that we are starting from this point and this point for beta 1, and we are taking very small steps towards different directions, and kind of we are trying to converge at the minimum point. So for beta naught we have converged at this point, and for beta 1 we have converged at this point. Obviously these two are different minimas. This is a different minima, this is a different minima. So these two are the different minimum points, and out of this then we can look for the global minima. But for now we will say that for beta naught we have reached different global minima, and for beta 1 we have reached different global minima. And this theory, it says that the image illustrates the cost function from a top down view. So we are trying to go towards the bottom, right? And the algorithm will reach to different local or global minimum depending upon the initial values, right? So it depends that from where you are starting. Maybe if you were starting from this point, then you might reach this side or maybe the other side. So depending upon your gradient, that on which direction you are going, so you might reach different minima, right? That's what is written. And the gradient in this context is a vector that contains a direction. So direction has to be there of the steepest step the algorithm can take, and also how long the step can be. So obviously now the steps might be big, So maybe you're taking this big step, right, every time, and then you're reaching, or maybe it might be very small, right, maybe 0.5 centimeter each and then reaching here. And I mean, you have different options. You can take small step or the big step, and we will discuss that what is the difference between taking small or big steps later on. But for now, we are just trying to converge to the global minima. And there are multiple concepts that they, I mean, you might get stuck in the local minima. There might be multiple minimas in the data set, and then I mean, you may not reach the global minima, and we will see that what has to be done in that case. But for now, this was the concept that needed to be told. So now let's discuss the I mean, this number of steps that they are there that we need to do for doing the gradient descent optimization. So in order to minimize any differentiable cost function, so this is very important. We need to minimize differentiable function. So it has to be differentiable at first place. So let's say that this was the function g of beta naught beta 1 up to beta k, and it had the multiple parameters k plus 1 parameters. And I mean, initially what you have to do is you have to initialize the parameters. Let's say that you are I mean, putting these parameters to a arbitrary value, maybe 0, right? I mean, why we need this value? Because we have to start from somewhere. You may start from here, you may start from here, you may start from here. So you have to arbitrarily start from some place. So that's why we have to give some value at the initial point, and then update the values of parameters. And I mean, we have to update it using this function, beta j equal to beta j minus alpha into delta j beta upon delta beta j. So what does this mean? Now here my alpha is the learning rate. Okay, so alpha is my learning rate, and we have written here that alpha is the fixed step size that controls the step size. And this delta j beta upon delta beta j is called the gradient of cost function. So these two things have to be multiplied and then subtracted from uh, the current beta j value, and then the value will be updated. And we have to move from j equal to 0 to k every time. So this update must be simultaneous. So when we are updating these values, we have to do it simultaneously for all the k values, beta naught beta 1 beta 2. So all of them have to be handled simultaneously, and this equation will be implemented for that. And so convergence of beta means that there is no change in the value of beta j, which will happen only when this slope is equal to 0. This simply means that, let's say that you were doing something like this. You had to uh, make the convergence for this. Let's say you were doing some uh, optimization on this plot, and initially some slope was coming out, but then there came a point when this thing became straight. And at this point my slope was 0. We can say that at this point my delta j beta upon uh, delta beta j will be 0. Why? Because slope is 0 at this point, because it is now parallel to x-axis. So that is what is written, that we have to converge at some point where this point has to give the slope of 0. This means that we have converged at the bottom point. Okay, so this last point meant this. And these are the basic steps. And simply you can say that initially you have to give the value to all the betas. Then you have to update the equation that we discussed here. Let's say that this was equation 1. So we had to update this equation based on the formula, and we have to stop our work. We have to stop updating this equation when we hit this point, when j beta upon delta beta j is equal to 0. When the slope is becoming 0, it means that we have reached the flat and maybe the plateau where my gradient is not changing. And so there is this intuition that I wanted to give you. So the intuition is that it may start from any arbitrary point, and it may converge at some local or global minima. Now just imagine that the graph is not just like this, but maybe it is something like this, right? And it has multiple minimas. It has this point, it has this point, it has this point. Out of this, obviously this one is the global minima, but your model may get stuck at this point thinking that yes, okay, this is giving me the slope of 0, and maybe this is the point. But right now we are not going to this kind of detail. We are just trying to understand that if the graph looks something like this and we have to reach the bottom point, then how this mathematics will work. For instance, consider cost function with only one parameter, theta 1. The shape of cost function is shown in the images 1 and 2. So the equation, uh, let's say that you have only one parameter for now, and your j theta is looking something like this that you have plotted here. But we will see that what is the slope on left hand side and the right hand side. So on the left hand side, because you're moving towards this direction, the slope will be negative. And if you are moving on this direction, then it will be positive, and we will see that how. If we start from theta 1 as shown in figure 1, let's say that it was this point, we were coming from this point, then the gradient delta j theta 1 upon delta theta 1 is positive. Therefore delta 1 is equal to this theta 1 equal to theta 1 minus positive quantity. Now because my gradient is positive coming from the right direction towards left hand side, because my gradient is positive, theta 1 minus positive quantity will be done for the update, and it will slowly move towards the minimum point because it is moving in let's say small steps. Right now we are not discussing the alpha value, but we are considering here as a assumption that we are taking small steps and we are slowly moving towards this bottom point. And if we look in figure 2, we are moving from left hand side to the right hand side towards bottom. And in this case what is being done is that gradient is negative. So because my gradient is negative in this case, overall my equation will become this. We wanted to do the minus of the value. So the equation was that we wanted to do the minus of alpha into this slope, but because my slope was negative, that's why it has become a plus sign here, and the value is positive now. So it will again slowly move us toward moving, it will start moving towards the minimum point. I mean, the idea is simple. You have to just remember that when we are moving from right to left hand side towards this bottom point, my gradient is positive. Okay, and if we are moving from left hand side to the right hand side, my gradient is negative, and based on that the equations have been given, and we are slowly moving towards the global minima. And why is learning rate fixed now? uh, I mean, it is not always fixed, but for let's say that we are fixing it, learning rate was the step size. So I told you earlier that how big step you are taking, that's learning rate, right? So, and in this case, uh, you can visualize that we are kind of making step size half every time. We are kind of making the step size half and moving towards this point. Okay, so we want to reach this point, but you may or may not keep the learning rate fixed. So let's say that we are making it fixed. So what we are trying to do here is gradient descent of algorithm can converge to a local minimum even with the learning fixed learning rate. So alpha is being talked about here. So as we approach a local minimum, gradient descent will automatically take smaller steps, so no need to decrease the learning rate over time. So now because you are finding the slope, and because that slope is changing every time you move this side, that's why even if you keep this alpha as a constant, I mean, let's say that it is being kept as 0.01 as a constant, but because my slope is changing every time, that's why overall my step size will become small. No need to keep the alpha as a variable. I mean, we do not need to make it every time half. Let's say that you are making this half every time, so that's not required. It just means that even if you are keeping it as a constant, then also the slope is taking care of the step size, because it is a multiplication factor here, and overall it will be affecting the learning rate also. So this is what I wanted to talk in the terms of learning rate. Even if we want to make it fixed, then also the step size is being affected accordingly, according to the way we want. Now, what if the learning rate is too small or too large? So on the left hand side in this figure 1, uh, we are trying to solve this. On this figure 1, we can see that if the step size is very small, it will take lots and lots of time to reach this point, because you are taking very small step to move towards this. And in case you are taking very big steps, then you might go out of this figure. You can say, you can see that it might be the case that you are missing the point, you are missing this minimum point. Yeah. So if the learning rate is small, the gradient will take lot of time to converge. So it will take lots and lots of time, because my gradient is also changing, and step size was kind of decreasing because of my gradient. But then if my alpha is also very small, let's say 0.00001, so if this is my alpha, and which is very small, then my overall step size will be very small, because the gradient is also changing, and it will take lots and lots of time to reach this bottom point. And on the right hand side, if we are, let's say, having a very big step size, let's say 0.5, this is very big compared to my alpha on the left hand side. uh, so we have to take care of this thing, and you might miss the bottom point. So you have missed this bottom point, you have not hit this point, just because you were taking big steps and you moved out of the space. So you have to take a very, you have to take a call on your end, that how much learning rate you have to use. Now, gradient descent for the SLR. So the cost function, mean square error function, for simple linear regression is dependent upon two variables, beta naught and beta 1, and this was the equation that we have already seen. And this gradient, I mean, I hope that you remember that this equation. And we knew that at in this equation, n was the total number of training examples, and dividing cost function by 2 will not affect the minimization process. So we did not have this 2 earlier. The equation was only this part, 1 by n into summation of this, but we have added this 2 just for the sake, because later on when we will be doing the differentiation, we will be needing to cancel out this 2 when it will be coming to the numerator on the left hand side after differentiation. So we will be required to cancel that out. So that's why we have taken the assumption of 2 in the denominator at this place. So let's see, what we are trying to do here is the gradient of the cost function is partial derivative of cost function with respect to input parameters beta naught and beta 1. So when we are trying to solve this, you can see that 1 by 2n is coming outside, and then you are trying to solve this equation. So this 2 will come out, right? And it is here now, so it will be cancelled. And now because you were doing it with the beta naught, so beta naught ke saath karoge, then you will find this thing, that when we are trying to do the differentiation on this, yi will become 0 because it does not have beta naught. This one will become 1, and again this one will become 0. That's why my this part will be giving me -1. So that's why my overall equation at this point is this: 1 by n into summation I equal to 1 to n beta naught plus beta 1 xi minus yi. So this is what we have got after doing the first differentiation with the beta naught. And then if we solve it with the beta 1 instead of beta naught, this time it will give me output of minus xi, right? So that's here, and all the other things will become 0. That's why it is minus xi at this point, and my equation will become this. So now we have to do the gradient descent optimization for the SLR. So initialize this beta naught and beta 1 as 0, and we have to update until the convergence point is found. So let's say that we have this temp 0 variable where my first equation is beta naught minus alpha by n into this point, and the temp 1 is beta 1 equal to alpha by n into this second point. So obviously I hope you remember the equation. So we needed to update the beta naught by doing this alpha into delta j beta over delta beta j, something like that, right? And we are just doing that same thing here, beta naught minus alpha into 1 by n of this part. Let's say that this was my equation 2. So this equation 2 is being used in this one, and this equation 3 is being used at this point. So it is using equation 3, and this one was using equation 2, right? So here beta naught and beta 1 has been taken as temp 0 and temp 1, and let's solve the numerical using these things now. So consider the following data set that shows the salary of an employee as a function of years of experience. For the given data set, show first two iterations of gradient descent optimization for linear regression, where we have these two values in the question that initialize beta naught and beta 1 as 0, and learning rate has to be 0.01. So alpha is 0.01 and beta naught and beta 1 are 0, and these are the, this is the graph, this is the Excel sheet that we have for our work. There is this one variable of x and one variable of y, and we have to implement gradient descent optimization on this SLR. So what we have to do is we have to first write the values, and we have to write the equations first. So beta naught and beta 1 are 0. This was the initial point, and second thing was we needed to update our beta according to these two equations. And for these two equations, we know that when we will be opening this equation, xi whole square will be used and xi yi will be used. So we have xi yi, we have to calculate xi yi and xi square, and we have done that for you. So this is how the updated table looks like, and we have to just now simply plug the values in. So alpha, we knew that alpha was this 0.01, so putting the value of alpha of 0.01 and everything, all the other values, we get the temp 0 as 454.44 and temp 1 as this. So we have beta naught and beta 1 as these two values, because temp 0 was beta 1 beta naught only, and this temp 1 was beta 1 only. uh, so this is how you have to calculate beta naught and beta 1. Then for the second iteration, you have to use the updated value. Now you have to put the updated value here of, beta naught will not be used as 0, but the updated value of 454.44, and in this case 4586.67. So putting the updated values in the second iteration, you are getting the updated values as 55 and 5418, right? So after two iterations, your values of beta naught and beta 1 are looking like this. Now if we do the same thing for multiple linear regression, everything is same, just that the beta values are more. Earlier my equation was ending at this point, that beta 1 x1, and everything was over. But now we have multiple values up to beta k xk, and the rules are same. We have to find the cost function 1 by 2n, and this thing, all the equation has been written as this. So 2 has been added again because for the ease of differentiation. And when you do it for the gradient, the equation will become this: delta g upon delta beta naught, and delta g upon delta beta 1 will look something like this. And similarly for delta beta 2, delta beta 3, but the general equation will be this. So if you solve all the equations, you will find that there is a pattern, and this is the general equation. Delta j upon delta beta j is equal to this, where beta naught beta 1 x1 i1 xi2 up to beta k xk minus yi into xij. So this is what we have got after solving all the equations for all the beta. This is the final updated equation of delta j upon delta beta j. Now we have to do two steps: initialize the value and update. Now initially we have considered that all the beta values are 0, and because the updating formula is this, that beta j minus alpha into that average, I mean you have to put this equation that we found, the general equation. So that has been written here. Now what we have to do is we have to solve it for a numerical where we have two variables, xi1 and xi2, and we have this yi, that is my prediction value that we want. So learning rate is 0.01 again, initial values are these, and what we have to do is you have to find the gradient descent optimization for the first iteration. Okay, so now you have to do only once, you don't have to do twice. Only one iteration has to be solved. So let's begin. Now we know that the equation looks like this because we knew that our general equation was this one, right? So this was the general equation. So for that we need the values of beta 1 xi1, beta 2 xi2, and you have to multiply them with the xij. So we have to take care of these things. Let's see how we do it. So xi1 and xi2, we had this y also. So these were the three columns that we had initially, but now we need xi1 into xi2, xi1 into yi1, into yi, xi2 into yi, xi1 whole square, xi2 I this whole square. So we are getting all these values because we needed to we need to substitute them in this equation. For first iteration we need to solve for this temp 0, temp 1 and temp 2. We are solving for three betas, so these three betas have been named as temp 0, temp 1 and temp 2, right? So these are the temp 1, temp 2, all the three temp variables are there. And now because you are substituting all the values, you have got everything in this table. So directly if you put the values, you will find that beta naught is coming out to be 11.19, beta 1 is coming out to be 24.46, and beta 3 is coming out to be 63.33. So these are the three values that we are getting out of the table here. So that's all. If you have any doubt in this numerical, you can ask.